when we see a problem involving more than one force, we know what to do. What do we do? If it involves one force, solve it. Go to your equations, write down your givens, solve it. But if you see a problem involving more than one force, what do we got to do first? Good, Jeremy. Let's draw a free body diagram. A free body diagram shows all of the forces acting on an object. It can show other things as well, like a mass or an acceleration, but it needs to show all of the forces acting on an object. Let's say we're looking at you in your desk. Okay, you sitting in your desk right now. Okay. Oh boy, I shouldn't have picked that one because that's a hard one to draw. Let's make it a box sitting on the floor. Okay. There you go. That's a pretty good box, isn't it? Let's draw a free body diagram for that box right now, just sitting on the floor. Give me one force. Give me one force. Yep. Good. Gravitational force acts which way? Good. Fg acts downward. And we don't know how long to make that right now. It's our first force, so the rest of them will be defined relative to that in terms of length. Yep. The normal force, which way does it act? Good. Goes upwards. Which way do you want me to draw it? Or, sorry, where do you want me to draw it? Position 1, position 2? Doesn't matter. Okay, let's draw in position 2 here. Is that a good length? Probably should be a little bit longer, actually, right? It should be the same length as the force of gravity. That's close enough that I probably wouldn't take any marks off on a test for that, because it's hard to draw it exact unless you're going to measure it with a ruler, and I've told you you don't need to do that. You don't need to measure it with a ruler. Any other forces acting on that box sitting on the floor right now? Nope, that's right. That's it. That's it. Okay, let's say that I push on the box and it accelerates towards the right at a certain rate. It accelerates toward the right. But there's friction involved as well. Okay, it's accelerating, but there's friction involved. Let's draw the applied force to the right. Now, we don't know how big the applied force is compared to gravity of the normal force, so that's the best I can do. Doesn't matter how long you make it. But there's a friction force. Which way is friction force going to act? Luca? Good. It's going to act opposite to that, so it's going to act to the left. Does anybody have an idea as to how long I should draw the frictional force there? Should I draw it longer than the applied force, shorter than the applied force, or the same value as the applied force? Why would you say shorter than the applied force? Okay, if it was greater than the applied force, we wouldn't say necessarily that it wouldn't be moving, but if it was already moving, it would be slowing down. Okay, when you put your brakes on your car, the frictional force is greater than the applied force. It's still moving, right? But the car is slowing down at that point, right? If the friction force is bigger than the applied force, it's not going to speed up, or it's not going to accelerate as I said it was going to in this case. It's going to slow down. Or if it stopped, it's just not going to move in the first place. We know it's going to be less. Let's change this question around a little bit. Let's say we've got this box sitting on a horizontal surface. This time, we're pushing on it with a certain applied force, but this time, it's moving at a constant velocity with that applied force. We've still got gravity. It's not changing, acting downwards. Whatever the mass is, times 9.81, we've still got the normal force, which in this case is the same value. And we've still got the applied force, which presumably it's going to be the same value here as it was before. What about the force of friction this time? Bigger, smaller, same value as the applied force. Remember, we're going at a constant speed this time, not speeding up or slowing down. Payton. The force of friction this time, when it's traveling at a constant speed, is going to be bigger than the applied force, smaller than the applied force, or the same size as the applied force? Good. Same size as the applied force. All right. In this case, when we go to analyze the problem, we cancel off the normal force and the force of gravity because they're equal and opposite, right? They balance each other out. We'd say F net is equal to the sum of the forces. In this case, it would be FF plus FA. And then we could, if we were looking for the acceleration, turn around and say M times A is equal to FF plus FA. Or if we were just looking for the net force, we'd skip that second step, just plug in our numbers and solve. In this case, we'd cross off this and this. We'd also cross off in this and this. There's not much of a problem there then, right? What's going to happen to this? Well, the acceleration is going to be 0. The net force is 0. There's not a problem because there is nothing to find if everything cancels out. Does that make sense? All right, we had a few questions for homework last night. One of them was directly related to this, and that was your practice problem on page 150 involving the bobsled. The second set of questions was some check and effect questions, a little bit more general in nature. We'll take a look at this one first on 150. It says, in the men's 4-man bobsled event in the Winter Olympics, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman is 630 kilograms. So listen carefully to what I just said there. The maximum mass of a bobsled with 2 riders, a pilot, and brakeman is 630 kilograms. Does it tell us that's what the mass of the sled, the pilot, the brakeman, and 2 riders is? Does it tell us that's what the mass is? No, it doesn't tell us that at all. It says that's the maximum mass that you're allowed to have. The maximum mass in an elevator, you go in an elevator and it always says like maximum 19 people or a mass of whatever. And I don't know about you, but I always think like, holy cow, fit 19 people in this elevator? Like, it'd be pretty cramped if you fit 19 people in this elevator. And if you did have 19 people in this elevator, the maximum mass isn't very much. Each person would have to weigh about as much as a 3-year-old. And if you got 19 3-year-olds in an elevator with no adults, there's a problem there, right? On a number of fronts. So the numbers aren't consistent. But the point that I want to make with this is that you're in that elevator, it says maximum mass is 800 kilograms, let's say, 800 kilograms. It doesn't mean that the mass of the people in the elevator is 800 kilograms. It means that that's the most you can put in it. That's what this is saying. It doesn't say the mass of this cart or this bobsled and the 4 guys is 630 kilograms. It says that's the most you're allowed to have. The most you're allowed to have in that elevator is 19 people and 800 kilograms. The most you're allowed to have in this bobsled is 630 kilograms. It has no bearing whatsoever on the analysis of this question, any more than if we were analyzing the elevator that we were talking about, the 800 kilogram maximum mass would have any bearing on the analysis of that elevator, unless you were actually at the maximum mass. That makes sense? 630 is irrelevant. So let's read the rest of the question. It says, during a practice run, riders A and B exert average forces of 1220 and 1200 newtons respectively. You know what that means, respectively? What's that mean? Yeah. Yeah, in the same order, yeah. So we've got A, then B. We've got 1220 that goes with the A, and then we've got the 1200 that goes with the B. Although that doesn't really matter in this particular case, which one you assign with which. Okay, that's what they mean by that. So let's say the force of A acting on the sled is 1220 newtons, and the force of B acting on the sled slightly less. We're going to say FB is 1200 newtons. It says the mass of the bobsled, pilot mass of the brakeman, 255, 98, 97. Doesn't see what the mass of the other 2 guys is. Doesn't see what the mass of the other 2 guys is. Or are. Is or are. We don't know what the mass. What's the mass of the other 2 guys? We don't know. Does it matter? So why doesn't it matter? Yeah. 2 of the guys aren't in the bobsled. Okay, they're pulling the bobsled, or pushing the bobsled, I guess it would be really, right? Okay, they're pushing the bobsled. It's this guy over here applying this force and this guy over here applying this force. Now, we haven't drawn it literally the way it would look, right? They're not pulling it by ropes, but we've said before, it doesn't really matter where you put the forces as long as they're in the right direction. The reality is they're standing beside the bobsled pushing on a handle, but it's easier to draw the forces right there, so that's where I've drawn them. The 2 guys, though, that are pushing aren't in the sled. They don't form a part of the system. They're like the tow truck pulling the car. Okay, it doesn't matter what the mass of the tow truck is when we're analyzing the motion of the car, nor does it matter what the mass of these two pushers is when we're analyzing the mass of the sled. All right, what mass do we use then? What mass of the sled do we use? Yep. Yeah, let's add all three of these together. We get 97 and 98, which gives me 195. 195 plus 255 is going to give me 450, I think. So let's say that's 450 kilograms. Now, I could write that down as a given over here somewhere, 450 kilograms, because the free body diagram technically doesn't include mass. But hey, I might as well write it down on the diagram. It's okay to add extra stuff. We just don't need to add extra stuff to the free body diagram. We got a force of friction acting here as well. It says 430 newtons. Which way is it? Which way is it acting? Well, it doesn't say, does it? Cassie? Oh, your hand wasn't up, was it? Oh, I'm going to call on you anyways. That's what you get for moving your pen around in your finger and making me think you're raising your hand. Cassie, which way does friction act? Sorry? Okay. Which way does friction act, Victoria? Backwards. It's moving forwards, right? Okay, you got these two guys pushing it forwards. Friction is going to oppose the motion, so it's going to act backwards. It has a value of 430 newtons, so it's going to be a much smaller force drawn to the left. Now, we do have a force of gravity acting on this guy, this sled. We also have a normal force acting on this sled, but assuming we're on a flat horizontal surface, which we got it here, then those two forces are going to cancel out, right? They're going to be equal and opposite, balanced. All right, now comes the easy part. Really is, really is. You just got to pay attention to some signs and not get your numbers mixed up, but really it's the easy part here. Let's say F net is equal to the sum of all the forces. Right now, you don't understand how important this is. Okay, by the end of Physics 30, you will understand how important this is. There are so many times in Physics 20, whether it's in the context of a bobsled getting pushed by a couple guys, or whether it's the context of a proton and an electron and another electron over there applying forces on each other, we ultimately do the same thing. F net is equal to all of the forces added together. This happens so much, not just in this unit, but so much in Physics 20 and in Physics 30, where we've got a free body diagram that may look completely different than this because the context is completely different, but the next step would still be the same. F net is equal to all of the forces added together. Okay, this is arguably the single most important thing. Arguably, because there's other important things, but arguably the single most important thing in Physics 20 or Physics 30, for that matter. Net force is all of those forces added together, the ones at least that haven't canceled out. All right, we're looking for the acceleration, so we're going to set that equal to m times a as well. Although if we're looking for the net force, we just leave it as F net. I think I said yesterday, some of you will probably, when you write a quiz or a test, which we're going to do tomorrow, by the way, write a quiz. Some of you will probably just skip that first step and go straight to MA is equal to the sum of the forces. That's okay. Okay, I can live with that. I don't want you to go straight to subbing in numbers. Okay, I got to see something up here, but I can live with going straight to this step. What's M? Well, 450. We figured that out a minute ago when we added those masses together. A we're looking for. FF, 430. Plus FA is 1220, plus FB is 1200. Is that good? Jared, is that good, or is there a mistake in there? Good? Is that good, Sam? No? Mistake? Good. 430 has to be negative because it's acting to the left. That's part of the reason I drew a free body diagram, right? Was so that I could see the directions. To the left, so we're going to make it negative. To the right, we're going to make it positive, although it's already positive, right? And to the right, that's going to be positive as well. All right, let's figure this out. 1200 plus 1220 is 2420 plus negative 430, 1990. 1990.